This video is part 2 of the lecture in section 7.4 on singular value decomposition from Math 311, a course in linear algebra at Western Illinois University. Before we get on, before I look at some examples, I just wanted to say one thing about the theorem at the end of the last video. Remember that you'll notice that these equations for these ellipsoids, they look like they don't have enough variables because these are equations in R variables. And I'll just say that maybe it should be a little more specific. Obviously, what we're saying is this article is obviously not in Rm. What we're saying, we might have to add a few zeros here, and then it will be either on the interior or a surface of an ellipsoid in Rm. An ellipsoid in Rm, of course, is going to be given by m variables, all of the form where the equation will be like x1 squared over some constant squared plus x2 squared over constant squared, and so on up to xm squared over something squared equals 1. Okay. So if you need to add zeros, that's fine. But the main thing is that the y's in this equation have to solve an inequality like this or an equation like this. Okay. So right now I want to do a couple of examples, and this first one might seem like a little stupid because it's the matrix is so small. But let's just go through the process of what we did. Okay, to find the singular values in the decomposition. So here we have consists of this is a 1 by 2 matrix first of all. So you can see that m equals 1 and n equals 2, and we have this matrix 2, 5. Okay, let's say we want to start by finding the singular values. So this is going to be a. We first find ATA. So this will be 2, 5 times 2, 5. And this will be a 2 by 2 matrix where the entries are 4, 10, 10, and 25. So we want to find the eigenvalues of this matrix, so we compute the characteristic polynomial. So we compute the determinant of 4 minus lambda 10, 10, 25 minus lambda. And this will be 4 minus lambda times 25 minus lambda minus 100. This will be lambda squared minus 29 lambda plus 100 minus 100. So those cancel out. So we just get lambda squared minus 29 lambda. And of course this factors is lambda minus 29. If you set that equals 0, so you can see the eigenvalues are going to be 29 and 0. So the eigenvalues, lambda 1 is going to be 29, lambda 2 will be 0 because we always order it so that these are in decreasing order, and this means sigma 1 is the square root of 29 and sigma 2 is 0, and these are the singular values of A. All right, now we want to find the V's in our matrix V. So we want to find the eigenvectors. So we start with lambda, the first eigenvalue. Lambda 1 equals 29. If we plug that into here, we get 4 minus 29 is negative 25, 10, 10, and then 25 minus 29, that's negative 4. So we want to find the null space of this matrix. Okay, and we can see that both of these rows here are multiples of. We can see that we can say minus 25x plus 10y equals 0, and then the other one is a multiple of this equation. And we can divide by 5, and we'll get minus 5x plus 2y is equal to 0. So 5x equals 2y. So think the easiest way to do this, if we want to avoid fractions, we can let x equals 2 and y equals 10, rather x equals 2 and y equals 5. That's what I meant. So that would be the easiest one if we want to stay in the integers. But then we want to normalize this, and the length of this will be 29, or the square root of 29, ironically, okay, which is not a coincidence. And then this is 2 over square root of 29 and 5 over square root of 29. And this will be V1. All right, then lambda 2 equals 0. Let's see what happens. We plug 0 in here. We get 4, 10, 10, 25. Okay, and then this becomes 4x plus 10y equals 0, and then the other this is just a multiple. The other equation will just be a multiple of this. So we can divide by 2, and you get 2x plus 5y equals 0. So 2x equals minus 5y. So in this case, we can get by if we let x equal 5 and negative 2, right? So yeah. That will do that if you don't want to avoid the fractions. And then we can normalize that again, and we'll get 5 over square root 29 and negative 2 over square root 29. And that will be V2. Okay. So our V will be this matrix. All right, now let's find what our U's will be. I should say that in this case, because we only have one non-zero singular value, we can see that R is going to be 1. And so we only have to compute U1. U1, which is going to be 1 over sigma 1 times A V1. This is going to be 1 over the square root of 29 times A times V1. All right, and all right, and now you'll see that this is actually just going to give us a 1-by-1 matrix, which is exactly what we expected, because remember m is 1 after all. So this is just going to be 1 over square root of 29. This will be 4 over square root of 29 plus 25 over square root of 29. And when the smoke clears, all this is just going to be 1. It's actually going to be the 1-by-1 matrix 1. Okay, so that's U1, and because we wanted this to be this is obviously a unit vector of R1, and this is a basis, an orthogonal. This whole thing will be an orthogonal basis of R1. So what we get, so we can say this is U1, and this will also be just the orthogonal matrix U. Okay, so the single value decomposition of A 2, 5. This is going to be the 1-by-1 matrix 1, and then sigma is going to be the square root of 29, 0, 0, 0. This is our sigma 1. This is sigma 2, and then this is going to be, and we'll have V transpose, which you'll see if you look carefully. This is symmetric, so V transpose is actually equal to V. So this is 2 over square root of 29, 5 over square root of 29, 5 over square root of 29, and negative 2 over square root of 29. Okay, So that's a single value decomposition. And then if we wanted to look at if x, let's say if x was just xy, we wanted to compute what ax was. This was 2, 5, xy, and this will just be a 1-by-1 matrix where the single entry is 2x plus 5y. And because what's going on here is the map that takes x to ax is really just a map from R2 to R1. All right, and so following what we have here, if because this is such a trivial composition, this is the same. Obviously, this is the same thing as this number 2x plus 5y times the matrix times 1, which is u1. So this will be our y1. Okay. So what we get is that if we restrict our inputs values to the unit circle, that is, if x if x squared plus y squared is equal to 1, then we get this value y1 divided by the square root of 29. This thing squared is less than or equal to 1, which is really the same thing as saying that y1 squared is less than or equal to 29, which is the absolute value of y1 is less than or equal to the square root of 29, which is saying that the absolute value of 2x plus 5y is less than or equal to 29. So geometrically here what we have is this, we've taken all the points on this unit circle here in R2 and we're mapping it to R1, and specifically we're mapping up to this interval, the square root of 29 and minus the square root of 29. We're saying all the points on the unit circle lie between these 2 points. All the points on here are taken by this transformation and put in this interval here. Okay. All right. Let's look at maybe a slightly more interesting example, which I've already started in your notes, if you take a look. All right, now in this case we have a 3-by-2 matrix. So in this case, M is 3 and N is 2. And we computed A transpose A, and we get this 2-by-2 matrix, 5, -4, -4, 5. We compute the characteristic polynomial, which becomes, after we simplify it, it's lambda squared minus 10 lambda plus 9. This, fortunately, it factors, and so the eigenvalues you can see are 9 and 1. And if you take the square roots of those, you get 3 and 1, and these are going to be the singular values of A. Then, if lambda 1 equals 9, we find the corresponding eigenvectors. You plug in lambda equals 9 in here, and you get everything is equal to -4. So that means 1, -1 is going to be has to be the eigenvector. And if you normalize it, we can normalize that and get V1. Similarly, if you plug in lambda equals 1 here, you get 4, -4, -4, 4. So it's easy to check that the eigenvector is 1, 1, and if you normalize it, you get this, which is will be V2. Okay, so we can right now we get that V is going to be 1 square root 2, -1 square root 2, 1 over square root 2, 1 over square root 2. So that's V. Now to find the U's. Filling in this formula, here's for U1, we get 1 over sigma 1 times A transpose, or times A times V1. And if you do this carefully, you can plot the 1/3 here, multiply this out. When you distribute the 1/3, 1 over 3 is the same thing as 1 over the square root of 9. And the square root of 9 times the square root of 2 is the square root of 18. So that's where the square root of 18 comes here. And then we do something similar for u2. This is 1 over sigma 2 a times v2. And this will just be 1 over square root 2, 1 over square root 2, 0. All right, so now that's u1 and u2. Incidentally, we know that r, we can see from here, r is 2, because we have two non-zero singular values. We need one more, because m is 3, and we need u3. So we need a unit vector which is orthogonal to both of these. Now we could use Graham-Schmidt, but the problem there would you need to find a vector which is outside the span of u1 and u2. However, this isn't too bad because essentially we just need to find a vector which is orthogonal to these two vectors, and we know how to do that, right? We basically want to we can reduce this to an earlier linear algebra problem, because you'll see that this vector u1 is really a multiple of the vector -1, 1, and 4, and this u2 is a multiple of the vector 1, 1, 0. All right, so we really just want to find a vector orthogonal to both of these. Okay, we want to find a vector a, b, and c that's orthogonal to both of these. So if it's orthogonal to this, we get minus a plus b plus 4c equals 0. And if it's orthogonal to this, we get a plus b equals 0. And basically, so this is just a system of linear equations. We can add these together, and we get 2b plus 4c equals 0. So 2b is minus 4c, so b is minus 2c. And it's easy to check that from here, a and b have to be opposites. So a is going to be minus b, so this will be plus 2c. And so we can let c equal 1, and we'll get 2, -2, and 1. Okay, and we can check that these are indeed orthogonal to both of these vectors, right? It's -2 plus -2 plus 4 is 0, and 2 plus -2 is 0. Okay, so we can take the u3 just to be the normalization of this vector. The length of this vector is the square root of 2 squared plus 2 squared plus 1, that's 9. Square root of that is 3. So this has length 3, and so we can take u3. We can just divide this vector by 3, every entry here by 3, and we get 2/3, -2/3, and 1/3. Okay, and that will work. Okay, so now we can let so that will be u, and so that our matrix 0, 1, 1, 0, 2, -2. The single value decomposition will be u, which is now consists of these this one -1 square root of 18, 1 over square root of 18, 4 square root of 18. So u1, u2 is 1 over square root 2, 1 over square root 2, 0, and then 2/3, -2/3, and 1/3. So that's our u. Our sigma consists of our values are 3 and 1. Okay, and then we have to add another, because in general with sigma, the dimensions of sigma are going to be the same as the dimensions of A. And then V just consists of, V transpose is the transpose of this vector. So the transpose is almost the same as this, it's just that these two elements are interchanged. So this is 1 over square root 2, 1 over square root 2, -1 over square root 2, and 1 over square root 2. And this is V transpose. Okay, and believe it or not, that's the decomposition. If you multiply this out, this does work. just say one thing about the this map. That map, there's a map so that this matrix A corresponds to well, if we look at the map that sends X to AX. Here we are talking about a map that goes from R2 to R3. In particular, what happens is we have 0, 1, 1, 0, 2, negative 2, x, y. This is equal to yx and 2x minus 2y. All right. And this is going to be, so this is going to be this is in R3, but it's really just going to, these actual vectors in this form are really just going to be linear combinations of u1 and u2. So this will be y1 u1 plus y2 u2, and we saw this before. y1 over let me just see here. Yeah, y1 squared over sigma 1 squared, which is, we said, is 9, plus y1 or y2 squared over sigma 2 squared, which is 1. This is going to be less than or equal to 1. Okay, so this is a so the image actually, is on the interior of this ellipsoid right here. Okay, so again, what's going on is that this is going to be here's R2, here's the unit circle. By the way, I should say if this holds if x squared plus y squared equals 1. Then that means that the points on this unit circle, well, here's R3, and in R3 there's going to be some plane that's generated by U1 and U2, and in this we're going to get this. This will be the points. So the points on this this circle and the unit circle in R2 are get sent to this interior of this ellipsoid, which is embedded on the plane in R3, within R3. Okay. And so that's what's going on. And so really this is this is all really I'm expecting you to do right now, is just identify the singular values, come up with a decomposition, and then understand what's going, what this transformation actually does. There's a lot of neat stuff that I'll be telling you about later on. But meanwhile, just work on these examples. Thank you.